A teaspoon of neutron star weighs 4 billion tons. That insane weight is real because atoms collapse into neutrons. We can map its inside like a layered city. Atmosphere, crust, core, and maybe something stranger at center. Here is the simple idea in plain words. Pressure squeezes matter into new phases with new rules. Each layer leaves a fingerprint in the signals we record. The picture gets clear fast once you know the landmarks. Start at the surface where heat glows in soft X-rays. That glow comes from a whisper-thin atmosphere, centimeters deep. Hydrogen or helium blankets the star, stripped by gravity. Light bends there so you see more than half. Beneath that atmosphere sits an ocean of ionized nuclei. Pressure crushes electrons into a degenerate sea, stiff as steel. The ions freeze into a crystal, a cosmic metal lattice. This is the outer crust, still made of nuclei. Density climbs beyond 1,000,000 billion kilograms per cubic meter. Atoms cannot exist here because electrons roam freely. Think of zinc, nickel, and iron nuclei squeezed incredibly tight. Why care about this layer at all, though? It controls how heat escapes and how fields anchor. A thicker light element blanket makes the star look warmer. Crust composition also sets the crust's strength under stress. That strength decides whether quakes crack or quietly creep. Numbers help here because the scale is brutal. 1 cubic centimeter weighs more than a mountain's block. Drop a marble, and it hits the surface near light speed. Gravity is about 100 billion times Earth's gravity. Even photons struggle to leave because spacetime is curved. Yet that delicate atmosphere tells us the radius today. By fitting the glow, astronomers pin down size and mass. Those numbers start the map that we are walking. Magnetic spots scorch patches, leaving hot poles that drift. As the ocean circulates, heat spreads sideways and fades. Impurities scatter electrons, changing thermal conductivity a lot. So the crust's recipe quietly shapes every X-ray pulse. That is why the surface layer truly matters. It sets the stage for everything buried below. Keep sinking and electrons start forcing neutrons out of nuclei. This is neutron drip, around 1 trillion kilograms per meter. Free neutrons flood the spaces, wandering through the crystal. They pair up and go superfluid, sliding without friction. Meanwhile, nuclei get weird because shapes lower energy. Spheres stretch into rods, then plates, then tubes and bubbles. Physicists nickname them gnocchi, spaghetti, lasagna, and waffle. These are nuclear pasta phases, born from competing forces. Coulomb repulsion pushes protons apart, while nuclear attraction binds. At crazy density, the tie becomes delicate and structured. Why does this pasta matter? Beyond being adorable names, it may be the strongest material in the universe. Simulations show a shear modulus that crushes steel by orders. It can hold tiny mountains just centimeters high for ages. Those bumps could beam gravitational waves if the star spins. Pasta also traps neutrinos, delaying how a hot star cools. And it can pin superfluid vortices, priming sudden glitches. We get hints from Vela, which jumps in spin abruptly. Its frequency rises by about 1 part per million. Then it relaxes over days as friction catches up. That timeline fits vortices unpinning, then dragging through pasta. Numbers again help, keeping scale honest in your head. Densities reach about 1 to 2 times nuclear saturation. That is roughly 2 to 5 times an atomic nucleus. You are basically walking through a nucleus now spread out. Electrons keep the charge balanced, streaming through like syrup. Meanwhile, nuclei drip neutrons faster and shapes keep shifting. The crust here hums with quantum motion and stress. Cross the boundary and the crystal dissolves into uniform matter. This is the outer core, mostly neutrons with some protons. Electrons and muons carry charge, keeping the mixture neutral. Neutrons pair and become a superfluid, flowing without viscosity. Protons also pair, making a Type II superconductor. 2 quantum orders now thread the star like hidden gears. Spin creates quantized vortices in the neutron superfluid. Magnetic field creates thin flux tubes in the proton superconductor. Each vortex carries a tiny swirl of angular momentum. Each flux tube carries a thread of magnetic flux. They can pin to each other and to the crust. When pinning breaks, angular momentum suddenly transfers outward. The crust spins up a hair, which we call a glitch. You can measure that from Earth with centimeter timing precision. Numbers help fix intuition when these words feel slippery. A typical pulsar spins tens of times each second. A glitch might change that rate by 1 part per million. The step happens fast, often within a single observation. Then the superfluid recouples and the star eases back. This dance times the friction and pinning deep inside. Meanwhile, the superconductor locks magnetic flux into quantized tubes. Motion of those tubes drags on vortices, coupling layers. If the core couples strongly, glitches relax more quickly. If coupling is weak, the afterglow can take months. Glitch catalogs now map friction, almost like seismic surveys. On paper, it is beautiful symmetry under crushing gravity. In practice, defects, heat, and impurities complicate the dance. That complexity is why long monitoring still pays off. Every glitch adds one more constraint on the unseen machinery. Bit by bit, the outer core reveals its rules. Picture a dark forest of vortices, all spinning in place. Each thread hums softly, while magnetic lines shimmer around it. Deeper still, densities climb beyond 2 or 3 times nuclear. Now the inner core may switch rules entirely. Traditional neutrons may share space with stranger baryons, called hyperons. Or quarks may unbind, forming a deconfined quark fluid. Either change softens the matter, making it more compressible. That threatens the maximum mass, which observations push above 2. We have a hard anchor, a pulsar at 2.1, so the inner core must stiffen again or avoid collapse. One path is a crossover, not a sharp phase break. Pressure could melt hadrons slowly into paired quark condensates. That state might be a color superconductor, exotic yet stable. Another path includes delta resonances and meson condensates. Each possibility reshapes sound, speed, cooling, and rotation response. We care because mergers and quakes sample those extreme rules. Tidal squish in a binary tests how easily matter deforms. If too soft, the star dents more under a companion. If too stiff, it resists and the signal shifts higher. Cooling of young stars also hints at new particle channels. Rapid cooling suggests direct Urca, which needs more protons. Color pairing could block that, slowing neutrinos dramatically. You see the loop closing as microphysics meets telescopes. The inner core stays hidden, yet its fingerprints reach us. Massive pulsars corner the options, forcing matter to hold firm. At the same time, radii near 12 kilometers guide stiffness. Together, those facts demand a balanced two-stage equation. Soft at mid-densities, stiffer again at higher densities. That pattern fits a transition toward quarks without catastrophe. Future colliders cannot reach these pressures, but space can. Binary mergers will keep squeezing and keep telling us. So how do we read layers we can never visit? We borrow nature's sensors, which the star already carries. Pulsations stencil the surface and let us trace shape. NICER times X-ray hotspots as the star whips around. Light bends, so pulse profiles encode mass and radius. Solutions point to radii near 12 to 13 kilometers. Gravitational waves add a second ruler during binary inspiral. Tidal forces squish stars, changing the chirp's phase evolution. From G170,817, the deformability sits in the low hundreds. That favors compact stars, not fluffy ones with big radii. Quakes and glitches bring a third probe like star seismology. Sudden spin jumps time the coupling strength in the interior. Free precession and crust oscillations hint at magnetic tension. Short bursts from magnetars add data on fracture thresholds. Put these together, and layers start to separate cleanly. Outer crust sets thermal glow, which pins radius estimates. Inner crust affects glitches, setting recovery times after jumps. Outer core stiffness shows up inside the wave chirp. Inner core choices nudge maximum mass and the merger fate. Observatories are still young, yet the progress is quick. New events will tighten errors and maybe split the tie. Here are a few anchor numbers to hold in mind. Mass around 1.4 suns, radius near 12 kilometers, tidal deformability between 200 and 800 today, surface hotspots near 1,000,000 Kelvin, spinning many times. No single number dominates, which keeps the field honest. Each channel cross-checks the others, layer by layer. Soon, third-generation detectors will hear softer, longer whispers. They will weigh pasta mountains or rule them out. And NICER successors will pin radii within a kilometer. That resolution finally picks winners among the inner cores. Magnetic fields lace every layer and they refuse to sit. In typical pulsars, fields run around 1 trillion Gauss. In magnetars, they leap to 10 quadrillion Gauss or more. That pressure can rival gravity, at least for the crust. Twisted fields store energy, which untwists in violent flares. One famous flare released about 10 to the power of 39 joules. That came from magnetar SGR 1806-20. Its crust likely cracked, letting twisted core fields snap back. Underneath, the proton superconductor forces magnetic flux into tubes. Those tubes pin on lattice defects, anchoring stress over decades. When defects fail, the star jerks and the magnetosphere screams. Even quiet pulsars carry tiny mountains on their crust. Super strong crust can hold bumps only millimeters to centimeters. Spin then modulates gravity waves, too faint yet for us, but limits already cut into models with huge deformities. Magnetism, superfluidity, and quakes are inseparable parts here. You change one and the other two must respond. That interplay is why magnetars are such valuable laboratories. Aurora-like arches may dance near the magnetic poles. Jerk events can also change spin down, briefly and oddly. That links external torque changes to internal crack dynamics. Thermal maps after bursts show heat flowing along field, so we watch surface scars to back out the wiring. If fields thread the core, precession should damp very fast. If fields stay in crust, damping should linger much longer. Current data hint at core threading, but proofs remain thin. Pause a second and let the star just breathe in silence. Its crust creaks slowly, while the core whispers below, unheard. A teaspoon weighing billions makes sense now, layer by layer. Atmosphere and crust set the glow and hold the quakes. Superfluid cores spin and stutter, carrying hidden quantum threads. An inner core may change phase, yet still hold firm. Together, those pieces write the pulses that reach us. If this map surprised you, come explore more with me. Tap subscribe and I will bring the next layer. The star is still talking and we can listen.